The topic of our project is estimating stock closing indices using a GA-weighted condensed polynomial neural network. We are a team of four. These are the contents we are going to discuss. For the introduction part, stock market prediction is critical for informed financial decisions, but it is challenged by high volatility and non-linear behavior influenced by economic, political, and psychological factors. With growing global investments, accurate and efficient forecasting models are essential. Linear models ARIMA and GACH are simple and efficient but fail with nonlinear volatile data. MLP and RBF and then handle nonlinearity but face challenges like overfitting, high resource demands, and slow convergence. Multilayer perceptron is a popular artificial neural network for modeling complex data relationships. It consists of an input layer, one or more hidden layers, and an output layer. Each neuron is fully connected to the next layer, enabling the model to learn patterns effectively. Radial basis function neural network have a distinct architecture compared to MLPs. It consists of input layer and hidden layer with radial basis functions like Gaussian functions and an output layer. The hidden layer computes the distance between the input data and center points, making it effective in capturing patterns. Next, my teammate is going to continue.
Forecasting stock market indices presents significant challenges due to nonlinear dynamics, volatility, and uncertainties inherent in the financial data. While traditional models are effective for capturing simple trends, they often fail to handle the complexities and rapid fluctuations that define stock markets, especially when dealing with the high dimensional and noisy data. This limitation underscores the need for an advanced methodology, one that balances accuracy and computational efficiency while remaining adaptable to unpredictable market changes. Such a model must reliably predict outcomes even under volatile conditions, which is the core focus of our proposal. Our solution is a condensed polynomial neural network optimized using genetic algorithms. CPNN employs partial descriptions to create polynomial based features that effectively capture nonlinear relationships. Instead of relying on deep multi-layer architectures, it simplifies computations with a two-layer design, ensuring accuracy without excessive complexity. Genetic algorithms complement this structure by providing a global optimization framework. Unlike traditional gradient descent, GA prevents the model from getting stuck in a local minima and significantly reduces convergence time. Through iterative process like mutation and crossover, GA evolves the optimal weights and biases for the model, ensuring robust and efficient optimization. Moving on to the advantages of the proposed model, the two-layer architecture avoids the complexities of the deep networks while focusing on essential polynomial features. This not only simplifies computations but also reduces the risk of overfitting. The use of partial descriptions enables the model to capture high dimensional patterns and relationships effectively, making it high suitable for stock market forecasting. GA-driven optimization ensures fast convergence, making the model practical for real-time applications in dynamic financial environments. This is the architecture of the proposed model. The input consists of the stock market data, including historical prices, trading volume, and technical indicators. The first hidden layer generates quadratic polynomial features through pairwise combination of inputs, such as x1, x2, and x2, x3. This helps capture key nonlinear relationships. The second hidden layer takes these inputs and generates higher degree polynomial interactions up to degree 4 to capture subtle and complex nonlinear patterns. The output layer combines and integrates these features to make a final prediction, such as the stock price or index value for the next period. Coming to the role of the genetic algorithm here, it plays a critical role by optimizing weights and biases across layers. It minimizes the prediction error using evaluationary strategies like mutation and crossover. Unlike gradient based methods, GA ensures global optimization, avoids local minima, and handles noisy nonlinear data effectively. Moving on to the workflow of GA, it uses the error between predicted and actual outputs as a feedback, adjusting weights and biases to minimize the error, improving the model's predictive accuracy over the time.
Experimental setting. Let's start with the dataset. The study focused on daily closing prices from January to December 2014 for 5 prominent stock indices: BSE, DJIA, NASDAQ, FTSE, and TAIEX. These indices were chosen to provide diverse market conditions and trends. To prepare the data, two techniques were used. The first one is sliding window technique. This technique was used to generate training and testing datasets. A window size of 5 was selected, meaning the model used the previous 5 days of closing prices to predict the next day. Every step of the sliding window created new training patterns, ensuring the model learned from a wide variety of historical data. And the second one is normalization. The sigmoid function was applied to a scale the stock prices between 0 and 1. In terms of testing, a separate dataset was created by sliding the window one step forward. This approach enabled the study to test the forecasting capability in real world scenarios where models predict based on previous unseen data. The study trained 4 distinct models: MLP-GD, gradient descent; MLP-GA, genetic algorithm; RBFNN, radial basis function neural network; CPNN-GD, gradient descent based condensed PNN. And the 4 key metrics were used to evaluate the models. The first one is MAPE, mean absolute percentage error. Lower MAPE values indicate better forecasting precision. POCID, prediction of change in direction. Higher POCID values reflect better trend prediction, which is critical for traders. ARV, average relative variance. A value closer to 0 signifies minimal variance, indicating the model's predictions align closely with real data. Thales use statistic. The value below 1 signifies that the model outperformed a random walk, validating its effectiveness. These metrics together provided a comprehensive view of the model's accuracy, consistency, and trend prediction capabilities. The table showing the performance of the forecasting models on 5 stock indices. The proposed CPN and GA outperformed the other models for all 5 datasets. The best ever statistic values are highlighted in boldface. For the BSA index, MLP-GA generated the best POCID value, it is 94%. For DJIA, FTSE, and TAIEX, the CPN and GA model performed better for all error statistic compared to the other models. Except for the few cases, the average forecasting performance of the CPN and GA was found quite satisfactory.
Coming to result analysis, this slide highlights the performance gains of CPN and GA model compared to other models that are discussed above in terms of mean absolute percentage error. The MAPE improvement is consistent across all 5 stock indices, showcasing the robustness of CPN and GA in handling diverse datasets. This chart demonstrates the percentage improvement in accuracy, making it clear that CPN and GA is superior for stock price forecasting. The graphs for each stock index show that the predicted closing prices using CPN and GA follow the actual prices very closely, even when sudden market fluctuations. The model successfully predicts the price direction, whether the stock price will go up or down, with high accuracy, as indicated by its high POCID score. The alignment between actual and predicted prices reflects the model's low MAPE, demonstrating its precision. The proposed CPN and GA model outperformed traditional models in terms of accuracy, as demonstrated by the lowest MAPE and highest POCID scores across 5 major stock indices. By leveraging quadratic and higher order polynomial features, the model effectively captured complex non-linear relationships and market trends. With an average computation time of 51.7 seconds, the model is suitable for real-time forecasting, an essential feature for financial markets. The deployed Mariana test validated the statistical superiority of CPN and GA model or the other approaches, confirming its reliability and robustness for stock market forecasting. For the future work, we can extend the model to predict other complex systems such as commodity prices, weather patterns, or healthcare data. And we can also adapt the model to handle even larger data sets and diverse time series types. These are some of the references that we use for developing this project. Thank you.